Okay, hello and welcome back. In this video we're covering section 4.2, which is a continuation of solving systems of linear equations, but this time we'll be looking at another method called the substitution method. Last time we were viewing systems of two linear equations as two lines, and if they intersect, then that point of intersection gives us an x value and a y value that solves both of the systems at the same time. And we were able to find that point visually by looking at their graphs, but in this video we're looking at a different method called the substitution method, which is analytical, meaning we won't be looking at the graphs, but rather performing some algebraic tricks that will allow us to solve the system. So let's look at an example. The textbook has this series of steps. Let's look at the example first and then look at the wording, how they describe the method. So let's look at this system. We have two equations, which I'll write them down. 2x plus 3y equals -1. And then the second equation is y equals 2x minus 3. So notice the second equation is already solved for y, meaning we have some expression that's equal to y. So the trick here is to take this expression, we want to substitute this We're going to substitute this in for y in the other equation. So what I mean by that is I'm going to rewrite the first equation, 2x plus 3y, but instead of y, I'm going to plug in this whole expression in x, because we're saying that's what y should be equal to. So 2x plus 3, and then instead of y, I'll put some parentheses and stick 2x minus 3 in here. And this is equal to -1. So notice we essentially got rid of the y's. We substituted in an expression for x into the y in the other equation. And that's where this term substitution method is coming from. Well, now we have an equation in one variable, so let's just solve this for x. So we will distribute the 3. So 2x plus 6x minus 9 equals -1. Then on the left side, 6x plus 2x is 8x, and then if we add the 9 over, we should get a positive 8 on the right side. So divide both sides by 8, and we get that x is equal to +1. We've solved for one of our variables. We have an x value of that point of intersection. So now that we have this, we can plug this in for x in either of the original equations. So I'll say now, plug this into one of the original equations. So I'm going to take the second one because it was already solved for y. That will make things very easy. But we could plug into either one. So it was y equals 2x minus 3. So instead of x, I will plug in that +1. So y equals 2 minus 3, which is -1. So we know that x is equal to +1, y is equal to -1. So our point, which is a solution, will be the point 1, -1. So it's a pretty tricky method. We solve one equation for one variable. In this case, that was already done for us. And then we take that expression and plug it in for that variable in the other equation, and that produces something like this, where you have now just a single variable that you can solve for. Once you have that solution, you can take that and plug it into one of the original equations and solve for the other variable. And we could check this by graphing if we needed to see that that is the point of intersection. Let's look at one more example, and then we'll review those rules listed above. So we have two equations, x minus 2y equals 7, and then our second equation, 2x plus 3y equals negative 21. So we need to pick one of these. This time we'll have to do a little work, a little bit of extra steps by solving one of these for one of the variables. Let's just take the first equation, bring it over here. So we have x minus 2y equals 7. Let's solve this one for x, because that looks like we'll just have to add the 2y over. So we can say x equals 2y plus 7. It'll be positive on the left side, on the right side. So now let's take what we just produced and plug it into the second equation. So I have 2x plus 3y equals negative 21. So instead of x, I'm going to plug in 2y plus 7, because that's what we're saying x is equal to. Then we'll have plus 3y equals negative 21. Now we have an equation just with one variable, so let's solve for y. I'll distribute that 2 through. This will become 4y plus 14 plus 3y equals negative 21. Then we'll have 4y plus 3y is 7y. And then let's go ahead and subtract the 14 over. Negative 21 minus 14 should give us negative 35. Then we will divide by 7. So negative 35 divided by positive 7 will give us a negative 5. So we have our y value. Now let's go and plug this into one of our original equations. Let's go to that first one again. We have x minus 2y, so instead of y, I'll plug in the negative 5 equals positive 7. So that looks like 2. Oh, and this should be an x, not a 2. X minus 2y equals 7. So negative 2 times negative 5 is a positive 10. X plus 10 equals 7. Then subtract the 10 over, and we get x equals negative 3. So x equals negative 3, y equals negative 5. So our solution point will be negative 3 comma negative 5. Or we can say that is the point where these two lines will intersect each other. So think about their graphs. So let's read through those steps that they've summarized. Let's go back up here. So to solve a system by substitution, the first step is to solve one of the equations for one of the variables. So we'll look at this first example. In this case, it was already solved for y. And in our second example, we had to do that, so it just takes a couple extra steps. We took one of the equations and solved for one of the variables. Then step 2, substitute the expression found in step 1 into the other equation. Then we'll obtain an equation that only has one variable. Then you can solve that new equation. That'll give you an x or a y value. Then take that value and substitute it into either of the equations to obtain the value of the other variable. So if we found x, we can plug that in to find y. And then we can check the values in the original equations to make sure that they work out and we get an ordered pair as our solution. So let's look at another example. This time it contains some fractions. This could apply to decimals as well. So let's look at our two equations. Our first one is 3 over 10 x minus 1 over 5y equals 1. Now we can go through that same process using, just working with the fractions, so using properties and rules of fractions. But we've learned previously in solving equations that we can multiply by the common denominator, and that will clear out all of the fractions. So let's do that. That'll make things a little bit easier on us. And it looks like if I multiply everything by 10, because 5 goes into 10, 10 goes into itself, we should clear out all of our fractions. Because this is like 10 over 1, 10 over 1. So the 10s will cancel directly on the first one, and then 5 goes into 10 two times here, and then we'll get 10 on the right side. So we should be left with 3x minus 2 equals 10. So this is our first equation. Let's do the same for our second equation. Let's go ahead and clear out the fractions. We have negative 1 over 12x plus 1 over 3y equals 5 over 6. It looks like all of these 12, 3, and 6, we can choose 12 as our common multiple. So let's multiply each one by 12. And again, this is like a 12 over 1. So the 12s will cancel. We'll be left with negative x on the first term. 3 goes into 12 4 times, and then 6 goes into 12 2 times. So this should reduce to negative x plus 4y equals 10. We got 2 times 5 there. So these are our two equations. So let's bring these together and look at it like a system. We've really just changed the way these two look. This should be a little bit easier to solve. So we got 3x minus 2 equals 10, and negative x plus 4y equals 10. And it looks like I left my y off here. Yeah, this should have a y. Lost track of this variable here. I was focusing too much on the fraction, so just got to bring that back in. So we have our system of two equations. We just need to pick one and solve for one of the variables. So let's pick that second equation. That looks like we can solve for the x pretty easily. So we can subtract the 4y over to the other side. So we can have negative x equals negative 4y plus 10. And then let's divide everything by negative 1. So that will flip the sign of everything. X will equal positive 4y minus 10. So we have one of them solved for x. So let's go back into the other equation, which was 3x minus 2y equals 10, and let's plug in this expression for x. So 3x, instead of x, I'll say 4y minus 10, minus 2y equals 10. So let's solve this for y. We'll distribute the 3 through. That will give me 12y minus 30 minus 2y equals 10. 12y minus 2y is 10y, and then we would add that 30 over, so 10y will equal 40. And then divide both sides by 10, y should be equal to 4. So there is one part of our solution. Now we need to go in and plug into one of these previous equations. So let's take this one that we already solved for x. That will make finding y very easy, because this is still equivalent to our second equation. We just move things around. So you can plug into this modified version. So we can say x equals 4y. Instead of y, we'll plug in our 4 minus 10. So x will equal 16 minus 10 or positive 6. So y equals 4, x equals 6. So our solution point would be 6 comma 4. So we followed the same process, we just got rid of the fractions first, which can make things a little bit easier. But we still, once we re-expressed our two equations, we took one and solved for one variable. So that's what happened here. Then we brought down one of the other original equations and plugged in our expression. And that gave us a solution for one of our variables, and then we went back and plugged that into one of our original equations and solved for the other variable. Now, if you remember from previous videos, there's a few special situations with linear equations where we might have no solution or infinitely many solutions. The case of no solution is when our two lines are parallel to each other. They have no intersection point on a 2D plane. So that case had no solution. Or infinitely many solutions if they end up being the same line. If they're on top of each other, then every point on the line is a solution to the system. So let's take a look at these two and see how these might show up without looking at the graphs. So we have our system. Let me rewrite it down here. 3x plus y equals 5. And then the second one, 12x plus 4y equals negative 7. All right, so let's pick one to solve for one of the variables. I'm going to choose the first one because that looks pretty easy to solve for y. We just need to subtract the 3x over. So y should equal negative 3x plus 5. Now let's take the other equation, plug in our expression. So 12x plus 4y, instead of y, we'll plug in negative 3x plus 5. Now let's solve for x, and this is equal to negative 7. So I will distribute the 4 through. So 12x, this will become minus 12x plus 20 equals negative 7. Notice the x's will cancel and I get this expression 20 equals negative 7, which is definitely not true. This is an indication that we will have no solution if you get something like this. There's no xy values that will solve this. So we've used this symbol from set notation for the empty set. We've also used the term inconsistent, and this might be a little bit more expressive of why we would use that term. It's an inconsistent result. So if you're in this process of solving with substitution and you end up with something like this, where one of your variables cancels and you get something that doesn't make sense, I would first just double check my work because maybe something went off, but if everything is correct, then you would just say there's no solution. You can stop there. All right, let's look at example 5. So we have our two equations. I have 2x minus 6y equals 10. And then we have x equals 3y plus 5. So it's already solved for x, so let's just take that and plug it into the first equation for x. So 2 instead of x, I'll write 3y plus 5 minus 6y equals 10. So let's solve for y. I'll distribute the 2 through. This gives me 6y plus 10 minus 6y equals 10. Notice the y's will cancel, so we get a similar phenomenon that we saw last time. And we get, this time, something that does make sense. 10 equals 10. So this is an indication that these are the same line. If we were to solve this first one for x, we should get the same thing. We can just test that. We have 2x minus 6y equals 10. Let's add the 6y over and divide by 2. X will equal 3y plus 5. It's actually the same line. So that's the case. If that is the case, there's infinitely many solutions. And we've used this kind of notation where we can say the solution set is all points x, y, such that, and we can put one of our equations, let's say, such that x equals 3y plus 5. Everything that is a solution to that equation is a solution to the system. And there is another term for this situation saying that the lines are dependent, or they are the same line. So the two cases where we end up with some statement like this where our variables disappear and it doesn't make sense, that is a case of no solution. Or if that same thing happens but we get something that is true, then there's infinitely many solutions and it's every solution to one of the lines because they are the same line. Oops. All right, I believe that was all for this section, another short one. So this was solving a system of equations via substitution. We saw a problem containing fractions or decimals, just had to clear those out, and then we can follow the same process again. And then there were those special cases for perpendicular lines, no solution, or I'm sorry, parallel lines that have no solution, or the case where it's the same line and there's infinitely many. Okay, that's it for this video, and I'll see you next time.